All right, I think we're live and we are recording. So, hello everybody. So, welcome to our Q3 event for GDG Cloud Montreal. We'll just go through some of the basic, and yes, I've recorded, so I'm good. Won't forget it. So, welcome to our event where we're gonna unleash the power of TPUs and reversionalize your ML pipelines with Vertex AI event. So, again, thanks for joining. We're just gonna go through some of the basic stuff, housekeeping. So we're just gonna do a little intro, like the TLDR, how to ask a question during the event. Then we'll just go full on with our main talk with David Cardozo, who joined us today. Simple stuff like hosts and speakers. I'm Stacy Verono from SC Cloud Experts, working from the office. So it's no shameless plug intended. It's our studio office, so that's why I have the logo in my background. I'm also with me. There's Florian Lee, who's from Davidson, Canada, and of course our main speaker. I'll just give some time to Florian to introduce himself because the beauty of this is that now I have someone with me to help grow the chapter for GDG Cloud Montreal. So, Florian, first of all, thank you very much for accepting the challenge of working with me on GDG Cloud Montreal.
Thank
And
you.
you already helped with the IU extended event that was in person not so long ago. So thanks for that. I'll leave you the floor to intro yourself.
Thank you.
Let's go.
So yes, first, thank you, Stacy, to give me this opportunity to help you for preparing those next event we will have for the GDG Cloud. So as you said, I'm Florian Lay, working for Davidson Canada. I'm a product owner and an analyst, and yes, I'm also passionate about the cloud and Google Cloud environment. So I'm really happy to be here as an organizer. We are preparing the next event together, so we will talk about that in few slides, or few minutes. So yes, that's it. Again, thank
Cool.
you, Stacy. So I'm really happy for that. Hope everyone will enjoy this presentation with David.
Perfect. Yeah. Thanks. Thanks again, Florian. So just a little housekeeping. Like since I changed the picture because of course they changed the entire interface not so long ago. So if you want to ask questions, like there's the chat option where people already saying hi to everybody. We also have like a Q&A section. So if you want to ask question during the event, I'm gonna start it. So I just started the Q&A, so you can go there. So Florian, myself, we can also like monitor this, and if there's any question like while David is presenting, we want to stop and answer. We'll pick it up from there. If there's any question that were not answered and we want to answer them later, then at least we'll have the information. We'll be able to post it in our chapter. So uh, it's pretty straightforward. Where housekeeping was short. That's the goal because this is going to be about unleashing the power of TPUs. You can see like the ML is nice to create image like the generative AI, but it still has problems even with the latest model in like writing stuff properly. But I still like the logo, so I left it there, even though there's ML twice. But anyway, so on to our main event, which is like unleash the power of TPUs, which is like reversionalize your ML pipeline with Vertex AI. I really have problems saying the first word, stumble upon it like twice. So I'll leave the floor to David Cardozo, who's the chief lead analyst and machine learning scientist at UpData, to go on with the presentation, present himself, and then just get us going into like our journey of TPU magic ML and Vertex AI on GCP. So I'll stop sharing so you can start sharing on your side. There we go.
For
So
sure. Thank you. So first of all, Stacy, Florian, thank you for the amazing work that you guys have been doing. I'm really happy that you guys invited me. So I hope I can share a little bit of things that I do find passion about. I really love about scientific computing, making things go extremely fast. So hopefully I will put a little bit of seed of curiosity for everyone in the chapter. So let me just start slideshow. Yep. Allow this time. Oops, give me 1 sec. Yes. Person should be.
Yeah, we can see you. We can see your
Perfect.
slide deck and yourself inside the slide deck plus on the side. So you have
I, I I have
double
triple.
David.
I have triple because I guess the slide photo also counts.
Yeah.
Uh, So yeah, long story short, so I wanted to start a little bit about this talk is a little bit more technical in the side that we're going to explore how these like things on the infrastructure plus the software that happens behind this kind of large language models. I just want to give you guys a preview of what is happening. Even though now machine learning seems to be moving that everything needs to be called an API, I want you guys to understand that there is no black box behind it. There is very simple mathematics and just scaling with infrastructure. And that's one of the things that I think Google can provide to help. And whenever you need to figure out that, hey, maybe foundational models are really not the answer for this, or I want to create a custom model in which I want to do really this extremely fast, but I don't have the GPU on house, or I just want to rent one from GCP, or get the new one. The I think it's the fastest hardware accelerator that you can get from anywhere is the TPUs, tensor processing units, and we're going to see that writing software for these things is not that hard, and at the end it's just mathematics and good software engineering practices. So who I am? Well, my name is David Cardoso again, 3 times for good sake. I'm a chief analyst at Data. We are a consultancy company in AI in Quebec. So most of our clients it's comes to us to do this scientific computing, machine learning, and AI part. And yeah, so we are in Victoriaville, in the middle of Centre Quebec. It's a city between Quebec and Montreal. And if anyone wants to taste the best cheese curds in the country, you should definitely have Victoriaville on your map.
Ooh,
Uh,
you're gonna start a fight now.
yeah, that's what I said in English. Anyhow, so I wanted to see, we're going to build a little bit small by steps, and we're going to see what is the main technology that happens behind these kind of large language models, and it's called JAX. So in the last 10 to 15 years, we have been building different kind of machine learning networks that have become like productionized. So we have TensorFlow, we have PyTorch. I don't know if people here have MXNext or Tiano. And most of the feedback that we have been gotten, or at least as a practitioner, is that sometimes it feels that you have to learn another language to like Python inside, another language inside Python for you to do effective scientific computing. So what we have done in the last few years is trying to get like a step back and think a little bit at the university or any internet course or everything. You mostly are exposed to scientific computing using NumPy, and the whole idea of JAX is that JAX provides you an API for array-based compute that is extremely similar, if maybe 101 with NumPy, a few asterisks over there due to actually performance. And it's that if you feel comfortable with NumPy, you can feel comfortable to doing machine learning. So you don't have to learn PyTorch or TensorFlow or this kind of like language in another language kind of tools. Apart from that, apart from like helping you to write this kind of algorithms in a language that you are really proficient, it also provides function transformation. So recall that in Python, functions are first class citizens. That is, you can pass through functions, you can serialize functions, you can give function to a function, right? And what we're going to see is that JAX will provide you auto differentiation. So if you are in your calculus classes, or if you don't recall calculus, you can write your function and take derivative, and JAX is going to compute it. That is going to compute that derivative, and you don't have to remember all your calculus course how to take a derivative. You're going to JAX is going to do it for you. So you write your code, and then you say, hey, I want to take the derivative respect to this parameter. JAX is going to do it. It's going to do just-in-time compilation. So I can say, hey, this code takes a long time. What if I just compile the function, and it will give me a function that is accelerated to CPU and GPU or TPUs without changing code. I also, if I have a code that only works in one example and I want to generate the code that works for a collection of those examples, I can vectorize the code automatically. And if I have multiple computers or multiple hardware accelerators, I can also map that code to different accelerators, and JAX is the responsible to do it. So people work very hard into providing the most optimized version, the most optimized code, and the only thing that you have to figure out is how to write the code for only one example. And of course, execute to CPU, GPU, and TPU without changing all the code. So if you're a PyTorch developer, it's going to happen, or hopefully you're going to see that it's that you have to do model to device if there is CUDA or there is not CUDA, or if it's another accelerator like in a TensorFlow Lite. So apart from that, JAX is extremely fast. This is MLPerf, which is a competition, a web competition for like you implement certain common machine learning algorithms, and you figure out and then you measure the time that it takes to evaluate. JAX is often in one of the top one categories for many of them. So if you implement in a residual network, sorry, it's not social, it's a single shot detector, a transformer, or a BERT, you're going to see that actually it's pretty, you can get extremely fast result and even more clean code than using JAX, TensorFlow, using JAX instead of using using JAX instead of TensorFlow and MXNet. And this kind of performance, you're going to see that it doesn't matter in which accelerator is going to happen. And we're going to see a little bit in the slides why that happened. So to motivate a little bit JAX, let us think about actually the simplest code that you do in machine learning is to implement multi-layer perceptron and MLP, or if you are from math, in the math side, it's like a linear regression with non-linear activation. My recommendation, if you are very I'm going to add here. Sorry, yeah. So I'm very fanatic of building small examples from scratch. This is from this advice comes from Joel Grus, which hopefully you guys could YouTube and Google for him. But he wrote a book that is called Data Science from Scratch, and it tells you that to be proficient in one thing, you should always make toy examples, figure out what is the mechanics behind that, and then use the abstraction. So we're going to follow the Joel Grus approach of how to learn JAX using very small examples. So what we have here is that if you're NumPy, this code should be very familiar to you. You import the library, then you define a function in which you pass some parameters and input. These parameters are the ones that with your machine learning algorithm you're going to tweak depending on how good and how bad goes into this loss function, which is the mean square error function. And you see that for each of these parameters, you're going to do a dot computation, bias, inputs, and then you return the outputs. And you're going to define how well and how bad does the selection of weights and biases is good. So hopefully this is not a very complex code. So let us take a look of what is missing when we do this kind of code implementation. So first is that if I want to run this on accelerated GPU, TPU, I will need to change this. So instead of using NumPy, maybe I have to use CUDA libraries. If I want to take, usually what you do in machine learning is that you take the function that tells you how good or how bad is it. You differentiate with respect to the parameters, and you say, hey, moving this parameter, it makes the model better or makes the model much better. And then you fine tune these parameters. And if I want to do auto differentiation, I will have to write my formula of the mean square error in the whiteboard and then take the derivative respect with the parameters. I took calculus almost 7 years ago, and I don't recall anything, so I prefer that the code does that. So if I want to do it in NumPy, I will have to do the calculation myself. Also, the compilation or fusion of operations, sometimes hardware has these dot operations and hyperbolic tangent at hardware. So if you do these kind of things, it will just dispatch only one operation. But in NumPy, here as it is, because because Python is very dynamic, you don't have any clue if you can do this kind of fusing. So if you know, you have to really go into the details of the hardware that you're using to to dispatch the correct operation. And of course, if I want to parallelize, if I write the code to only one example, how I can do it for many in a list, or how I can do it if I have multiple computers that we are going to use. So next, what we're going to do is that how we do it with JAX, and you're going to see that using JAX is very simple. Is that you import the library, and then you can just change jax.numpy as np. So there is a namespace in which you have a copy of the NumPy API there. From JAX, you see that the code doesn't change. You bring the same operations, dot, tangent operation. And what is going to happen is that if I want to take the derivative, I can use the grad function. So I pass the grad function. I evaluate grad on the m squared error. And what I'm going to get here is the derivative of the function with respect to the parameters. So in here, I already have the function without me calculating the derivative manually. I can JIT it, and that's going to see that, hey, do you have a GPU? Do you have a CPU? Do you have a TPU? And then I can have the function that is optimized to that gradient function. Also, if I want to do for a list, I want to calculate the gradient with respect to a list. What is going to happen is you are going to take a mini batch of your sample data, and you want to evaluate that in just one single run. You can vectorize that grad function and then just JIT it, and then you say, hey, in the axis, don't differentiate with respect to the first parameter and the second one on the axis of the array. And then if I want to just use all the parallel device that I can do it, so each of the devices is going to have a copy of this grad function. Then in each of them, I'm going to have the JIT version. So I will have the optimized code in each of the computers that is connected to it. So take a look that I didn't have to change anything of my code. I just used the functions transformations. And this is something that hopefully it's one of the key ideas is that Python code will be traced to an intermediate representation that will be dispatched in a very optimized way. This same immediate representation will provide you with access to the XLA, which is the Extreme Linear Algebra Compiler, and that technically you can use it as a black box, and then you don't need to know all the things that happens behind the curtains, but you can get this optimization for free, and you can hook up any of your functions at any of the steps. If you want the compiled version, if you want to vectorize, or if you want to have the gradient calculated. And it's a powerful set of composable transforms. Doing research on JAX is very, 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 very simple. So if you want to take anything about JAX, just take this slide, and we're going to see what's happened behind the curtains, and we're going to see how the optimization happens behind. So how does JAX works? And I wanted to ask to the audience is that what this function actually does. So hopefully you're going to see. Oops, sorry. Hopefully everyone will say like, yeah, it takes something and then add to. But if you're a Python developer, Python is very dynamic. We don't know what X could be. So I can add something very, I'm not saying that I'm a rogue actor or something, but if I wanted to do something evil, I can just take an object, right, the espresso maker. I can overload the plus operation, and then I can just do a sub-process that open SSH to your machine, something like that. No, I'm not saying that I could do this, but I could, right? Because of the dynamism of Python that allows you to do that. So I never know until I evaluate the function what is going to happen. And if you think that this is something that nobody will do, I will invite you that like the tar XS vulnerability was something like that, like in something that allows you to unextract files. You saw that there was someone injecting code that will allow to connect to SSH to any machine that had the software. So it's not something that it's taken out of a fantasy book. So as you can see, this dynamics of Python, this dynamic part of Python makes that you don't know what is going to happen with the function until you evaluate. And this could be any object that you can have there. So what we have done is that we can actually take advantage of this dynamism. And what we're going to do with JAX is that we're going to evaluate this function on a tracer value. We're going to record all these operations, And then after I pass once, I already know what the function is going to do, and we can use this kind of information to compute. So just this is not exactly what happens, but the mental model is actually pretty similar. You define a separate object, you define what happened in each of the operations, and then you record the operation as soon as you evaluate it. So whenever f happens, you compute, hey, what was my D type, if it was a float 32, float 16, or B float 8, and then you record all the operation that is happening over there. So what is going to happen with these tracer values? So let us take a look a little bit more of what happens when you evaluate the logarithm of 2 in JAX. So we're going to import lags. So this namespace inside JAX gives you access to directly to the XLA compiler. So all the operation here, you can think about it of one-on-one mapping with what is happening on the hardware from Python. So that's pretty cool. So what is going to happen is that if we define this function log of log base 2, I'm going to define the input, which is going to be a. Then I'm going to define, I define another function, which is the log of this number, which is the part, then c, this 2.0, and then I return the value, which is the division of b and c. And the thing that you have here is what is called a Jack expression, a Jack XP if you read on the internet. And this is the code that the compiler will make sure to make the automatic differentiation, to batch and parallelize, and to just cheat it. So here, as soon as you evaluate the function once, you have the trace value, and these trace values allows you to have this kind of all the function compositions that you need. And yeah, so that's what is happening behind the curtains. And it's this kind of mechanics is injected in the whole ecosystem of JAX. So what you can do is that you can just JIT it, and they will give you the JAX intermediate representation. And as soon as you have the intermediate representation, you can also have the high level optimization. So the compiler will read this JAX expression and then dispatch all the most accelerated function that you can have on each of the hardware that you can have. And then you can calculate the gradients and the virtual and the vector map of this. So where this is used, there are a few things that real case nursing which just have been used. One of them is to classify and to pick up the triage, separation of trash. Sorry, uh, generation of diffusion models, right, and proof of concept of segmentation. And since these machines use different hardware, the same code that you use can actually be given to any kind of this robot. So JAX it's already something that is being used to solve real problems. So if you are convinced, now we're going to step a little bit back into the black box to how to scale this code, and let us take a look at flags. So JAX and flags, the relation is that JAX sometimes is very low level for you to do your own algorithms. You also want to have a library that allows you to have all the layers that Gemma use. So if you use the open source model of Gemma, you want to not re-implement Gemma from scratch. You want to already have layers that someone else has written. And this is what flags is going to be. So for those that use already TensorFlow, you can see NNX as you can use flags as the keras for JAX. So for neural networks, flags expose a subspace which is called NNX, which is come from neural network X, and it's Pythonic. You're going to see that as soon as, if you know keras already, this should be very simple. It's simple. You're going to see that we're going to do a very small example in a few minutes, and integrates years of user feedback. So let's take an overview of how this actually works. So every layer is going to be an NX model. You initialize the layers that you want. If you want a layer that with input features 5 and then outputs 10 output features, is going to be defined like this. You pass your random number generator. random number generator are something that it's that is provided by JAX, and you're going to see that this is important if you want to replicate results. Sometimes, as machine learning engineers, we don't recall that people need to replicate their experiments. It's part of the scientific method, and JAX ensures you that using specific random generators, you will always get the same outputs. So if you can see Pensai, you can actually, with Pensai, which is a new library from Google to observe how the numbers of each layer of each model works, you're going to see that the bias is a number of zeros, which is the D type, and the kernel, the cool thing is that you can actually have visualization of what is happening on the layers of the neural network. So if you are interested about, I will share these slides in a few minutes, but if you are interested in how these random numbers work and everything, you're going to read it here. And the whole thing is that you define a model, then you define the attributes that model, which can be layers, which can be input output functions, by nonlinear activation. So everything you put it is just in the same essence of PyTorch and Keras. You define a init and then you call in this kind of part. So let us go to an example. So now I'm going to see how we can do this in a collab. We're going to install flags, the pen side to see an observation, and then a library to track all our metric, all our experience of that. What we're going to solve with JAX today, with flags today, is going to be the TensorFlow. The
Sorry, David.
TensorFlow. Yep.
Sorry, I don't want to cut you off. Is there a way you can zoom in just a little bit?
Yeah, for sure. That's
Oh,
good.
that's way better. Thank you, sir.
Yeah. So we're going to see that we're going to solve the CFAR10. So the CFAR10 is the Canadian the Canadian data set of 60,000 images of 32 by 32 images into different categories. And what is going to happen is that we're going to calculate we're going to have, no, thank you. No, it's okay. So yeah, so sorry. So we bring the data sets of the CFAR10, the train and the test. I already calculated this before, which is the standard deviation and the mean. So recall that in machine learning, you always have to normalize your input so you can converge very. It's a good practice to do it. We're going to define our data engineering pipeline, which is we're going to use TensorFlow dataset to it. We're going to do by 32 batches. We're going to see our dataset 6 times. And we're going to take each of the images. We're going to divide by 255 because these images are uint8. We're going to take, we're going to rest from the mean, and we're going to divide by the standard distribution. So we have a normally distributed dataset. Apart from that, everything that we do on the train, we're going to do it on the test, all right? And then we're going to see how the NNX part is going to work. We're going to define something very, very simple, a simple convolutional neural network. So you're going to see that the layers are very similar to what you find on Keras on PyTorch. You have a convolution, you have an average pooling, you have a multi-layer perceptron. You define your models in the init code, and then when you call, you just apply what you want to do. So first a convolution, then a ReLU, then an average pooling, then finally again a convolution on the output of this, then the average pool, then you flatten your properties, then your ReLU, and then you end up with the logit of 10, which corresponds to the log probability of the object being in that class. And if we use PenSci, the thing that is really cool is that you can see the modules, how they were created. So the convolution is an array with full of zeros. The kernel is not all zeros, because in CUDA you don't have a square matrix, you have real matrices, but you can actually see how the values of the convolutions work. So if you are interested in learning how convolution works, you can actually see the kernel maps of this and the linear. So finally, if I want to evaluate, let us create an image of 32 by 32 sizes with full of ones, and the model will think it's actually, I think it's the biggest one would be 0.42 for the category 7, I think. Yeah, So the cool thing is that you can actually also see what Tensai is a very cool tool, and NNX and JAX it's already integrated, so you can see what is happening on your neural network. You can define optags, which is the part of the library that Google provides for the optimizer. So you keep your functions, you define the loss function, you define your train step, which is jitted. So I want to make the train step goes fast, then to evaluate, and we're going to calculate on the time. So what is happening here, this is the code for training, which we're going to scale up with TPUs at this moment. Right now, recall that I'm using a CPU, I guess, manage session. I'm using, I'm using a CPU without GPUs. Look, that is taking me to go to an epoch. I'm starting at around 145 seconds per epoch, which is not that bad. But if you are doing, instead of 60,000, you're doing a million of images, every second counts. And I get this kind of visualization. But let us change to what actually happens when I use a GPU on it. So I'm going to stop sharing because I'm going to share my screen, entire screen, this one, this one. So I already run this code on a T4, which is a GPU provided by Colab. So you're going to see that I have my GPU. And the same code, no changes. I did Control C, Control V, copy. I go to 145 seconds to 9 seconds and 9.46 seconds. Okay,
Can you zoom in again, or just a little bit? Sorry.
Excuse. Ça te
Okay.
correct?
C'est parfait,
Ok.
merci.
D'accord. Fait que, sorry. So we reduce from 145 seconds to 10 seconds to 10 seconds per epoch.
Sorry, I'm going to cut you off, David, again. There's a question in the chat, so I don't know if you're able to answer. It said like the code and everything, it looks very similar to PyTorch. Wondering what's the difference.
So here in PyTorch, I didn't have to specify the model to device, right? I just, the only thing that I needed to compile is NNX jitted. So I don't have to do model to device and figure out if I have CUDA or not. I never had to deal with any of the prerequisites of using a GPU. And if you are using a TPU, when you do this in PyTorch, which is what I'm going to show in a few minutes, you need to modify your code. And the whole thing is that your code should be similar if you're running to CPU, to GPU, or TPU. And the whole idea is that the only thing that you should care is that to write your model. Is that something that the AI cannot do right now, right? To create automatically the architecture, something that you want to say, something that you want to implement. So the whole thing is that here, what JAX provides you, it's going to be the same NumPy code and the same as any hardware accelerator. So yeah, in PyTorch, we're going to see a few differences. Just give me a few minutes when we go to the TPU, and you're going to see if you can do this on PyTorch. I'm really happy to see how you will do that in PyTorch. So right now,
Perfect.
10 seconds. Also the speed. I'm pretty sure that I can get to 12 to 13 seconds in TensorFlow. I don't know if I can get to 9 seconds with a very simple convolutional due to the overhead, but JAX overhead is very, very minimal. So 9 seconds and 9.5 seconds, and it get exactly fast. So now that we have this, so I made the resume here. 15.70, and then I go to 9.74 seconds, same code. Now, what about TPUs, which is the way that I wanted to, the crux of this talk is that, so TPUs are hardware accelerators designed inside at Google. This is a picture of probably one of the pods that trained BERT at the time, well, now Gemini, right? and each one of these has almost, I think it's 123 teraflops and 250, which is faster than any GPU that you can find. And then it's only 1.1 petabytes of data at a time. So if you want to do something that is very compute intensive, you can do it. You can do it in here. So how does it work behind the curtains? I'm just going to pass about this very, very quickly. But the tensor processing unit work as a very specific hardware accelerator that can do matrix multiply in very, very, very fast time. It's actually a new kind of architecture, which is kind of systolic array. Systolic is because it works similarly as the heart works. So you put your inputs, you divide this in batches, and these batches goes past to each of the tensor processing unit. Through the high communication part, you can just multiply, aggregate, and recall that in the matrix operation, you can break it up into slices of matrix and vector multiplies, and this is extremely, extremely fast. So here, the only way to get a TPU actually is through the offer of Vertex AI. I'm not going to cover a lot of Vertex AI. I'm just going to cover a little bit that is called pipelines here. But pipelines, you can see it as a scheduler for all these kind of services that GCP provides you. And actually, what is happening behind the curtain is that pipelines allows you to have an access to like the internal Google Kubernetes engine service that is running Kubeflow. So it's very cool because this is actually managed. You don't have to deal with installing different nodes machines, trying to figure out if the quota is all right. It's all provided by Google and managed by Google. So it's really cool if you don't have like a large team to maintain a Google Kubernetes engine service. So pipelines, you can see it as an orchestrator that runs Docker containers. So I can describe it as a direct acyclic graph in which each of the nodes it's a Docker container. And each of these Dockers, you can specify to Google, hey, give me a GPU to this, give me a TPU to this. And also these containers provide artifacts. So if you are doing an item classification, you can do, you can do, hey, output the confusion matrix after this container has trained a model, or after pre-processing, just show me the statistics of the data set. And this combination of this stack, which it looks huge, but it only consists of three things: Kubeflow, Docker, and Python. And we're going to see how we actually can do the same in Python. So this is going to be example reference that we're going to do. We define a component that has this Docker image, which is just the pip install JAX and pip install. So a Python container that only has JAX and TPU and all the requirements to visualize the data. Then we define this as a container component. Then we pass this component to a training job, and we request a machine type. This is the TPUs v5, which are 3 times much faster than the one that I show in the picture. How many TPUs you can have? You can have 4 or 5, and they work in nodes, so you can have like a very complex topology. 150 gigabytes of data, and then the pipeline just call this part. If you want to do like more complex stuff that apart from training, as soon as the model is trained, you can deploy it and everything. You can do it on this kind of pipeline, and it's going to be very simple. So what is going to happen? I have here. Hopefully I learned to do the Zoom correctly. So if we define our pipeline, so this is very Python code that only requires a Python and Docker. You define your component as a Docker. You define, hey, what is the command that I want to do? So I'm going to call the bash, the shell sh -c. So you're going to tell it this input evaluate python.train py. So the train py is on the image, but I want to show you that it's actually the same code I just did download from Colab without me to modify anything. TensorFlow data sets, and then the train. Exactly, I just copy. I didn't modify anything at all. Then after I created the task, I defined the project in which this pipeline is going to run. The location, TPUs are only in US West and some regions in Europe, so that's the only thing to take into account. Then I'm going to call the Kubeflow compiler, generate a pipeline. So if we take a look, this Jamal, it's actually similar to one of Argo. But the cool thing is that as a data scientist or as a machine learning engineer, I never had to deal with Argo to call the Kubeflow installation. No, this Jamal is the one that you're going to upload to Google Cloud Storage to evaluate. And if we take a look at this, I'm going to show you in my project. I create the component training job task. If I take a look at the node, pipeline job, oh, sorry. Then I reduce the time of 150 seconds to 5 seconds. Previous run were around 471. I don't know what changed. Um, but I will blame who I can blame here. Hardware. Data scientists always blame hardware when they don't get the results. Yeah. So just to run it, that will be it's only create run. Then you upload the file, you upload the YAML to that, you define the configuration, and that's how or you can just clone a previous experiment and then wait. And as you can see here, if I take a look at the type of the machine, is this CTL5LP high TPU 1 tera with a topology of 1.1. You can do cool things like create 4 and using jacks and then parallelize this kind of part. And yeah, so we reduce the time from 150 milliseconds to 478 without me doing knowing like modifying my code to know exactly where I run. Just I let jacks and flags do all the hard work. So I think that'll be it. I know that there is a lot, but I hope I leave a little bit of curiosity for you guys to see it, to go a little bit apart from the calling the APIs of Gemini and part to try to implement your own LLM. Use Google to scale your machine learning compute. And yeah, I always put things that go wrong when doing the demo. So sometimes you're going to see that the resource exhausted, that there is no more TPUs to Google to give. It's not that expensive. I think this experiment cost me $1.29 Canadian. So I don't know. I don't know how that is in American dollars. If you are interested of doing this kind of work and you have projects that you want to experiment, I'm always coaching people. So just shoot me a link in part, and I'm here for questions. So we reduce the time of 150 seconds to 7 seconds to train a model. So no code modifications. We just took Google and then we just scaled that service. So hopefully this they will give you ways to make machine learning more faster. So I think that will be it for me.
Cool. Well, thanks a lot, David. Like I know that the answer you gave to the question that I asked was bang on. So it said like handsome, like awesome, got it. Thank you. So that's great. Since what we still have some time, just wondering like we're just gonna open the floor to questions.
Mm-hmm.
And if the people actually, I think everybody can say raise your hand. I'm not sure. And if it's easier to say it versus type it, I can actually unmute people. So if somebody wants to like to ask a question, maybe just like say it in the chat and I can unmute you if you want to. And we can go like this if there's any questions. So we'll open the floor, and we'll see if there's no question because everything was so crystal clear for everybody who understands. um, all right, so we do have a question that was typed by the same person.
Mm-hmm.
So I don't know if you're seeing them. I'm not sure, right, David, on your side, if you're looking, seeing the chat. There's the chat bubble at the bottom left, right before the
Okay,
mute
okay,
and
okay.
stop video. So if you click on it, you'll see a question that you can do
Yeah.
it on multiple
So
GPUs. Yeah.
yeah. So this is fine. So I will say it so that everyone can see. So you mentioned it that it could be done in multiple GPUs. I'm wondering how is the parallel done? There might be many different strategies. How does it choose one? So for doing like you can do worker and then multiple workers and then you consume the gradients. For that, I will give you the if you're interested in how to, you can actually implement your own strategies, but everything the magic of doing this dispatch the code to multiple devices done by the parallel map part. So here's a very simple strategy that you actually copy the code on that, and then you can actually there is uh, there is functions that do all reduce, so you compute and then you all reduce and then goes to the same worker. But also this pmaps is give you that the code is in each accelerator. You can also do like things on hardware and then just wait at the end, the wait at the end to collect all the results. So what you can do is actually you can implement your own strategies. You are not focused. You are not limited by the framework. So there are also another libraries that build on this kind of stuff. And if you want to do like only one worker and the other only one, sorry, master and the other one the workers, and then yeah, you can do it in your part. So the thing that I want you to take is that you can pmap. You can do that. You can read on the pmap documentation that you have multiple ways, and you can say, hey, I want this code, but don't collect until I do the following part. And doing this kind of distributed computing is also one of the secrets of JAX, but that requires another presentation that hopefully, Mr. If you're in Montreal, I will invite you that you learn and teach us how this kind of parallel synchronization works. With all the pleasure, Mr. Jisupeng. Hopefully, I'm pronouncing that right. To unmute, Stacy.
Thanks for that. So yeah, maybe we'll be able to get you on our next event where it's going to be like more of a all the Google communities across Montreal during the fall. Maybe you can do it show even more like on stage. Any other question? If there's Angie said yes to that. So so, so yeah, so like if there's no other question, here we go. Does TensorFlow work with this as well?
So I don't understand what do you mean by TensorFlow. This way, I don't need TensorFlow at
I
all.
think in
This is
the
like a
parallel mode,
replacement.
probably, right?
In the parallel mode, you can do, but recall that TensorFlow actually force you that before you do the strategy. So doing things like, hey, I want this function to be run on the following workers. You have to modify your code that is not it's not very, or for me at least, it's not very simple to have control. Hey, I want to, I don't know, all the workers that are even, I want just to do gradient something, or take another batch. TensorFlow is very limited in this part, which I think is the whole reason that a Hugging Face accelerate tries to obscure these kind of things. But TensorFlow only force you to have one strategy. The whole thing with the PMAP, which if there is interest, I could show you. I could create a slide to see how this actually works on cloud. We can create very very difficult, like advanced techniques on how to allocate this code to different devices. But yeah, this is a more advanced talk. I want to feel if it was too much for the community. If it's not, then we can for sure do this kind of parallel stuff, a workshop in the future.
Cool. Yeah, and honestly, like that's the thing. Where there's generic topic where we'll have like a bunch of people coming in, and then we can zoom in on something and go super deep. Then of course it's going to be a specific story, but it's always a story that's worth sharing, because there's always someone who's going to end up with, it's like, how do I do this? Well, yeah, well, there was like a specific event tackling this. We went super deep. It's always welcome. So something to keep for the future. Cool. So I'm gonna restate. If there's no more questions, I'll just wrap things up. Then I'll just ask you to stop sharing, David, so I can share again. Oh, there, that's Angie now has a question, but that's good. How do you try Jax for recurrent tasks?
Uh, First of all, thank you, Andrew, for coming. Thanks very much. In recurrent neural networks, since there is a part that I didn't say, that JAX is a very functional programming paradigm. So that means that you try to avoid side step. When you are doing recurrent neural networks that you want to save the state, you have to, that the only you will not use JAX pure. You will use an NX namespace similar, sorry, flags NX model that saves the state for you. but it's the same. You create example for only one, you vectorize, you instead of using JAX bmap or JAX JIT, you use nnx jigs and nnx bmap. So, and instead, JAX will not work directly with something that saves states because it's very functional programming. What you're going to do is call nnx that has JIT and JIT pmap and bmap, specialized things that save state. And the whole magic of how that works is something that is still a work in progress, and it's something that the Google DeepMind team is actually putting a lot of effort into make this as simple as possible. So for recurrent neural networks, use NNX at this moment, but the API will change a little bit in the future. But yeah, I'm fan of the attention mechanisms that makes everything much simpler instead of saving state. But that's a hot take. That's a hot take in the future. With all the pressure, Angie. Thank you very much.
Cool. All right. So I'm back with the video. Um, yeah, we're still gonna. Is there any other questions pending? Feel free. We still have time. Like I said, if not, we're gonna wrap things up. And you can always join the conversation on Discord. So I'm just gonna share this. I'm wrapping things up. I'm having way too much fun with ideogram running on GCP to create images. But anyway, so yeah, we're just gonna wrap things up. Just gonna make sure there's no other questions. All right. So again, like I've mentioned, you can join us on Discord. You go to the GDG Montreal chapter. So they are hosting the Discord instance, and we are a channel on that. So you can just go with the QR code or there. We were on Slack before. We still are, but there's kind of a shift to Discord. So feel free to join us there, and then you can ping us. So future events. So everybody is always asking like, when's the next one? So the next one's already planned. So we're gonna do this. The event is not up yet. It's gonna be up soon. So September 12th at Davidson, Canada. So Florian is gonna host us directly into their office. So we're gonna talk about GKE Enterprise in action and more. It's still open to other topics. And at the same time, if you ever want to submit a talk, you have the nice little QR code there. It's gonna notify us that you want to do a talk. You can also like reach us directly on Discord or even LinkedIn. That's what we're here for. So make sure that we're getting. It's always nice to get speakers from the community. It's nice to have Googlers, but it's also nice to have like people actually play with this in real life. So that's our next event coming soon in September. The other one is DevFest 2024. So last year we did it at McGill University on a Saturday. This year we're still looking for a spot. There was a possibility at the Google office, but it may be too short on like space because we're targeting probably like 200 people. So now we're looking at other venues in Montreal. So it's gonna happen October, November 2024. So we'll have DevFest 2024, which is gonna cover everything from like the Android community, like Flutter is gonna be there, WTM, like the women tech makers are gonna be part of this. Also, GDSC from McGill, from Concordia are gonna be part of it. We are gonna be part of it, and also our GDG Montreal chapter team is going to be there. So keep an eye out. We'll update you. Sorry, with more details there. So before I go to this one, so there's gonna be a where's the recording? So you just have to give us the time to like download it from the platform, re-upload it to YouTube. And then now the beauty is that YouTube accepts, and also since we've switched to something that looks like Google Meet embedded inside the Bevy platform, you're gonna get a 1080p recording, which is way cooler than 720p when you're sharing your screen, especially for code. So keep an eye out. So that's going to be soon, and as soon as it's posted, it's also going to be posted in the on Slack, but also uh, on Discord. So again, I want to thank everybody who joined us. Want to thank David again. Thank you so much. We've been chatting back and forth on LinkedIn. It's super nice to have you join and present. Um, it was super insightful for people like myself. Like I play in GCP every day. That's what I do. But that was like the ML part. And that's really something where I play a lot. So it's always nice to kind of say, hey, by the way, like there's this world also that leverages the platform, does many things, and this is how you could do it. So thanks. It was super insightful. So thanks for that. Thanks for your time, Florian. Thanks again for joining the team, and looking forward to even more events in the future. So we're like I said, look for us for September. We're gonna send this out, put the event live as soon as everything is set up, and the rest, well, keep an eye out for our more info on the uh, DevFest 2024. Sorry, I was looking for that. As soon as we get more details. So on that part, I'm going to stop the recording. I'm going to stop sharing and stop the recording. And thank you all. And we'll see you next time. Bye, everyone.
Thank you, everyone.
Thanks, David, again.
So with all the pleasure.
All right. Bye bye.